Hello. My thesis is on implementation of a fourth microcontroller core in an FPGA. Here you have the HANA 1 architecture, and if we had an hour to study it, you would notice that there's no register file. There are stacks, but no register file, and that's because this is a stack machine. What is a stack machine? Well, many programming languages are actually stack-based. Python, Java, Ruby, PostScript, WebAssembly. Wikipedia has a long list, maybe close to 100. Let's take a look at one of them. Python, it looks like a normal programming language, 10 plus 5 times 3. But if you actually look at the disassembly, um, first it pushes a 3 on the stack, then it pushes a 10 on the stack, then it pushes a 5 on the stack. It does a plus operation on the top two items, giving you a 15. Then it does a multiply operation on the top two items, giving you a 45. And finally, it prints it. There's actually a language optimized for a stack-based computer called Forth. So in Forth, you type 3, 10, 5 plus times print, typically dot for print. It's an interpreted languages, so that does the same thing, gives you the 45. Why would we be interested in Forth? Well, because of the power issues. So this is a chart of power for different operations in an ASIC. If you look at the bottom two, the most expensive ones are reading of memory on chip, and even more expensive is reading of memory off chip. That's actually a logarithmic scale. If you look at it in a linear scale, on chip memory access takes 5 picojoules, off chip memory access takes some 640 picojoules. And that makes sense because off chip on the board, you've got these much larger wires. The capacitance is just much larger. So in order to minimize the energy consumed, you really want to minimize the size of the memory, and stack machines do that for you. So let's compare stack versus register machine instructions for an ALU operation. On the bottom row, we have a RISC-V 32-bit instruction, 32 registers. To specify one register takes 5 bits. To specify the two operand registers takes a total of 10 bits. Destination register is another 5 bits. That gives you 15 bits for the instruction, and we haven't even specified what the operation is that's going to execute there. In contrast, ALU stack-based machines like microcore and UXN do very happily in 8 bits. And so because they don't have registers, they just have a stack. All operations are on the top of the top two elements of the stack. And so they're much smaller. Actually, in EP16 and B16, you can fit 3 operations in a 16-bit instruction. EP32 fits 6 instructions in a 32-bit instruction, 6 operations in a 32-bit instruction. So you can see why stack machines have much smaller memory. There was actually a book on hardcore stack machines. There are 66 known softcore stack machines. Most have been forgotten. The most important ones that people are still talking about, I reviewed in my thesis. Really interesting to see how all of these differ and the different ways that they're things that they're optimized for. The most popular is the J1. To understand it, you need to understand memory types. So we have single port memory, one read or write per clock cycle. We have dual port memory. 2 ports can both either read or write during one clock cycle. There's also something called pseudo-dual port, where one port can read while the other port can write during one clock cycle, but you can't have 2 reads and you can't have 2 writes. And the reason that's important is to understand the J1 family, there are a lot of different versions of J1. There's Verilog, VHDL, Spinal HDL, and Scylla. There's 16-bit, 32-bit, 64-bit. There are dual port, pseudo-dual port, but there's no single port version. Oh, okay. So I built a single port version. Actually, I started off with there's J1, and then based on top of that, we get MeCRISP versions. I started with the MeCRISP pseudo dual port RAM, but it's way too complex. So I switched to doing it started again from the MeCRISP dual port, and then created HANA 1 processor. Okay, so what's the issue? If you look at the old processors, they had 32 of these BRAMs, block RAMs, each had 4 kilobits. That gives you 128 kilobits. There are 8K words. You have 16 bits each. The newer devices, the ICE40 Up5K, they got these big single port RAMs. It's twice the memory of the entire older device. And what that does is it frees up all the BRAMs. And so then you can use 2 BRAMs for stacks. And in fact, it turns out you need a third one for bootloader. So what are we doing here? Here we have the data read and write. On the left, we'll take a look at the data reads. Basically, your program counter is going along, and at some point, um, you give the program here on the address line, you give the program counter to memory. It comes back with an instruction, which is the read instruction. On the top of stack, you have the address. So in the next clock cycle, you basically pause the um, instruction updating. And the next clock cycle, you give the address, look at the edges at the beginning of the clock cycle too. You give the memory the address, it comes back with the value. And then at the end of that, at the end of clock cycle two, beginning of clock cycle three, it replaces the top of stack. There's something similar, a little bit more complicated for data writes. And here we have the Verilog for reading. We have a pre-memory read value, which is a wire, and then a reg, which is memory read. If you look at the last two lines, when do you know it's a memory read? When the previous one was a pre-memory read. Okay, how do you know it's a pre-memory read? Basically, the instruction says read, it's not a memory read, and it is an ALU instruction. Then you get the pre-memory read. So pretty simple stuff, something similar for writing. At first, I used the iVerilog and doing some printing of what goes on the UART, but you can't run an interpreter on top of Verilog, so that got tossed out. Next, I ran the Verilator. It's actually mcrisp ice connects in with Verilator, but the problem is it didn't connect and it couldn't generate the files to drive GTK wave. So I added all of that with an option. You don't want to be writing to your disk too much, so there's an option to dash trace that I can use to either save the files for Verilator or not. Okay, so the other thing you need to do is initialize the memory. It turns out single port memory you can't initialize it in the bit stream, so you have to do something else. So the obvious thing, if you read the manuals, it says that during warm boot, the single port RAM is preserved. So basically, you just run a simple core, you copy in all the data, and then you run the final, and then you do a warm boot. You have all the data in the SP RAM, and so then your runtime core works. Great, perfect. Except for it didn't work. No matter what I did, I just couldn't get it to work. I couldn't figure it out. So, okay, what do? All I had was a 8-bit logic analyzer. These are 16 bits wide chips. I want to look at multiple signals at the same time. So what I did is I just put I put two soft cores in. One was a working soft core and the other one was a broken core with a single port RAM. And the working core had a regular clock. The broken core could set the clock. I set the value, look at the requested value, and very quickly I saw that the problem was with the single port RAM. So this was quite easy, but to see the results. What was difficult was to actually do it because you have to use the same source code for the Verilog, but generate two different circuits off of that. And of course, I didn't want to do that. So I had to write some Python to be able to create two different versions, and then I could merge those together into the final circuit. Okay, so then I fired up 4 SPRAMs and, okay, with all the read, write, sleep, wake, standby, reboot options, because I had the interpreter, so I could do things, I could test it all out very quickly. And okay, clearly something is wrong there. I did a single port. And what I was able to demonstrate is that warm reboot simply does not save it, right? You write a script to copy the data in, you do a warm reboot, all the data, boom, gone. And so a lot of people have tried to do this. Actually, nobody had succeeded. Even we reported this through the board vendor to sort of priority partner technical support at Lattice. They had never heard of anybody who actually succeeded to do this. But because I had such a good test environment, I could demonstrate that actually the single port was not working. And so I was able to dig into the documentation. It says that it works, but actually, if you read the standard configuration, the beginning of the configuration, all the SRAM has been cleared to 0, and on power off, this pin turns off the power to the memory core. Note that there's no memory data retention when this is driven low. So just even the documentation is inconsistent. So this all got reported. Unfortunately, I don't think they've done anything to change, but I did create a video about this. Also, somewhere along the way, I wrote up tons of documentation about all the microSPICE stuff, particularly the cross compiler is incredibly difficult to understand. Okay, but I still have to do the booting. So what you do is you do a bootloader. So there's an SPI, there's basically an SPI bus. It's a bit complicated, right? So there's SSRAM and the RP2040 on it, and the FPGA and the SPVG flash, and there's some PMODs and some other pins that display. And so you need a diagram like this to understand, because what happened previously, people just had circuit diagrams like this for all the different pieces. And not only did I end up frying a circuit board, but even the experienced board designer, he got it wrong because this is not very clear. And so they had to do another rev on the board design, well before my time. So this diagram works much better. Okay, so how do we actually initialize it? Well, remember we have this fourth core, and it's got shift in and shift out, and so just use it, right? So we have a little one of these tiny 4 kilobit params. We write a little program. It sets the instruction 03H, which says shift, which is the instruction for give me some data to the flash. It gives the top 8 bits, and then we shift out the next 16 bits of the address we want to do. And then if you look below, the data starts coming back in. We get basically two bytes and another 2 bytes, and then we can write that to the SPRAM. And then you basically just loop through this and do it again until you've copied it. It doesn't take long. The software environment is rather tricky. There's an instruction set which is modified. There's the nucleus. You have to use a cross compiler that then gives you enough to load code. So then we use the simulator to load the code. There used to be ice cream machine, but I tossed that out. Just replace it with a Verilog simulator. And then some of that goes into Flash, and it needs to first of all be converted to binary and then converted to another format. So when you load it to the RP2040, it gets loaded into the appropriate address on Flash. Part of it is just the hex file gets loaded into the bootloader. Of course, creating the tiny bootloader program is a little bit tricky, but that's another story. Also for debugging, I had to do to load the flash just with some numbers 1, 2, 3, 4, 5, 6, 7, just so I could debug that all the reading and writing over the flash was working correctly. So complex software that the bootloader is very small. We basically just here we have the single port RAM, and in front of a tiny bit of the thing, we put one of the single port RAM, we put a bootloader, and then we boot from that address, and it copies all the data in. Here's the boot program. Fourth, completely incomprehensible until you learn to be a fourth developer. Yeah, it's really quite easy, very elegant. So there are some interesting results here. The J1A has a great reputation for being a really small CPU, comes in 1100 thing. microSpice, well, they use way too many, they have way too large stacks and done in lots. So okay, that's way too big. But HANA 1 PSRAM, I could move those LUTs to the BRAM, so that made them a lot smaller, or just a tiny bit bigger than the J1A. But once I moved it to SPRAM, boy, it shrank, and suddenly, boom! I didn't realize this at first, but I got rid of that whole enormous multiplexer tool that merges all those little BRAMs together. Now, the microSpice HANA family has like 26 instructions, so it's fundamentally and interrupts and all kinds of other stuff. So it's really fundamentally much bigger than the J1A. But if I use that SPRAM on the J1A, I can shrink it down to like 900 LUTs, maybe actually about 200 LUTs less, 950. And that's going to be way smaller than any of the RISC-Vs. So that's going to be a really important paper. This part got accepted to conditionally accepted to Euroforth, but the next ones are going to be really a landmark paper. Okay, we still have a couple of minutes. Professor Milik was very interested in the sort of the Python stuff and how you convert from languages. Here we have the ALU instructions. 3 bits say it's an ALU instruction. 5 bits gives you which opcode it is. 4 bits do like return, some write, a couple other things, functions, return stack, data stack, changes. And so based on how you configure these, you actually get what are called delighted words. So on the left-hand column, you have all of the normal instructions, but then you get to do you can get much more complex instructions where the CPU actually does multiple things at the same time. So that brings us to 14 minutes and 20 seconds. Here's the HANA 1 architecture. Do you have any questions? Thank you.